In this video, we will continue getting some practice writing proofs involving functions and sets. So in this video, we're going to focus on proofs involving the inverse image. Recall in a previous video, we looked at the image, or the direct image mostly. So let's start with the following example. We'll let f be a function from a to b, just any two sets, and we'll consider two subsets this time of b. So b1 and b2 will be subsets of b. And here's what we want to prove. Prove that if b1 is contained in b2, then the inverse image f inverse of b1 will be contained in f inverse of b2. Okay. So let's recall what this means really quick. This inverse image. This is not the inverse function. This is so b1 is a set. So this is just a notation meaning the following. So let's just recall if you have any subset of b. So if T is a subset of B, then we define this F, -1, F inverse B, F inverse T. I mean, you can also define F inverse B, but this is more general. So this is, what is it? Well, T is over here, and what you're doing here is you are considering the set of all elements over here in A that map to T. So in other words, this is going to be all the A in A such that f of A is in T. That's the inverse image. Very, very important construction here. So inverse image of T under F. Okay. So let's get some practice with this definition. We're going to try to prove this. So if B1 is contained in B2, those are subsets of B, then the inverse images sort of respect that containment. So here's the proof. How do we start? So we should always look at what we're trying to prove, develop our strategy. So we're trying to prove if something, then something. That's an implication. If P, then Q. So what do? We assume P, we assume this, and we try to show that. That's the whole strategy. Let's just inform the reader what we're doing. So yes, we're going to assume if B1 is contained in B2. And we want to show this. Well, what is that thing that we're trying to show? It's a subset containment. So I want to prove that's contained in that. How do you do that? You take an arbitrary element of this one and then show us in that. Okay, that's how we prove a subset containment. So here's where I'm going to start. I'm going to take an arbitrary element of here. So let x, or what can we call it? Where does this live, by the way? This lives over in A. So maybe I'll call it little a. It's a good idea to name these based on where they live. Like if it's over here. That will help me to avoid getting confused later. Like if I called this little b, I would probably get confused later because little b is actually living over here. So it's just I mean, I'm not saying the proof would be incorrect, but so there's often a choice to make it easier for you to follow. So let's let A be in this set. And what do we do now? Well, we have the rest is just going to sort of unravel from this. So we have the right setup here. That's the most important part. How do you get started? This is how we're going to get started. We're going to take an arbitrary element here, prove it's over there. Let's unravel this definition. What does it mean for A to be in there? So by definition of the inverse image, that means A. What can we say about this A? Well, it maps to B1, right? So f of A is in B1, right? But B1 is contained inside B2. So since B1 is in B2, f of A is also in B2. Right? It's an element of B2. But we're basically done. Because what does it mean to be in here? In this set, it means that f f of that element is in there, in B2, right? That's what it means. F inverse of T is all these things in A such that f of A is in T. Well, we just proved f of A is in there. What does that mean? So again, by definition of inverse image, so I'll say therefore, this element A is in f inverse of B2. Okay, so this is a really good proof to sort of nail down this concept of inverse image, because we're sort of using the definition 2 times. First, we have A is in this inverse image. We have to write down what that means. Here we identify, so this is what it means for A to be in the inverse image. So we're kind of using it backwards here. But yeah, this is a good proof to go over a few times just to make sure you understand all the steps. But we are done, right? Because we showed that our arbitrary element's over here. Let's do another example. So the same setup. So let f be a function from A to B. And let B1 and B2, again, we have these 2 sets in B. And I want to prove, this time, an equality of 2 sets. So I want to prove that f inverse of B1 intersect B2 is the same as we do f inverse of B1 and then intersect that with f inverse of B2. Now, this might remind you of something from the previous lecture, where we had the same thing, except with f inverse we just had f, so we had the image. And in that case, it was not an equality. It was actually just this was contained in that, but you don't get that contained in here. So apparently when we do inverse images, it's just an equality. So both are contained in the other. Let's prove that, though. And I already hinted at how we'd prove it. How do you prove an equality of sets? So first we'll show the forward equality, forward containment. So say we'll show this is contained in that, and then we'll prove that's contained in that, and that proves they're equal. Again, very clean way to prove 2 sets are equal. So let's take an element of this first one, and I'll call it A because it lives over in A. Okay, take an element of this, and then we'll write down what it means to be in the inverse image. I am not thinking hard yet. I'm just unraveling the definition. So what does it mean for A to be in here? It means that f of A is in B1 intersect B2. And I'm still not thinking hard because I have another definition to unravel. What does it mean for f of A to be in there? It means that f of A is in both B1 and B2. So, and f of A is in B2. Okay, now maybe I'll start thinking. So I need to show that my A is in this and that, right? That will show it's in this intersection. But wait a second. I feel like I'm almost there, right? Because what does this first one say? Like, does this say that A is in f inverse of B1? It absolutely does by the definition, right? So again, by definition of inverse image, I'll say therefore. So you don't have to repeat this every time you do it, especially if the reader is well aware of what this is. But sometimes it's good to point out. So you can say by definition of inverse image, for example. It means A is in f inverse of B1, and A is in f inverse of B2. So F is so A is in the intersection. That's all there is to it. Okay, intersect f inverse of B2. Very nice. We're not quite done. We've shown we've done half of the work. So next, we'll show the reverse containment. We'll show that this is contained in there. So you can write it this way if you want. So we'll show this is contained in there. So we'll let A be an element of this one. And you might say, well, yeah, can't we just reverse all the steps? I feel like we can, actually, in this case. These all feel reversible. Let's still be a little bit careful, because remember last time, seemed like maybe we could reverse them, but we couldn't in one case, like if this was replaced by F, not F inverse. But what does it mean to be in here? It means that A is in both of these. And yeah, I think we're just going to end up reversing the steps. So A is in F inverse of B2. What does that mean? Let's keep unraveling the definition. Again, this is a great one to do for practice, just to make sure you can really understand this definition. So what does it mean for A to be in here? So we can say by definition of inverse image. Inverse image. It means that if f of A is in B1 and f of A is in B2, so f in particular, f of A is in B1 intersect B2. B1 intersect B2. And we're done. Because, well, we're done after we say, therefore, again, by definition of inverse image, A is in. If f of A is in here, that means that A is in. Right, A maps into here. So A is in the inverse image of B1 intersect B2. Excellent. We've shown both containments. And again, you can often add a sentence to the end, just letting the reader know, oh, because we've shown both containments, that proves the sets are equal. Okay. We've done enough of these that, yeah, I'm not going to explicitly point that out. But let's do one more. So this one gets a little bit interesting. Let's let, so f will be a function, and how should we do this? So, and we'll let T be a subset of B. So I just have one subset of B this time. And then we want to show that. Actually, we'll do two things. So we have a two-part problem. So number one, let's show that. Show meaning proof. F of F inverse of T. This one's going to be tough to unravel. But this thing, there's an inverse image inside a direct image, inside just the image. So we want to show that actually that's contained in just the set T itself. So let's see, wait, does this even make sense? T is over in B. F inverse of T, that's going to live over in A. It's going to be some subset of A. And then F of A, yes, that will live back over in B. And we're saying that's actually contained in what we start with. So you might be wondering, why isn't that equals? Or is it equals? Or if it's not, is there some condition maybe on F or T that can make that equals? In fact, there is. So part 2 is going to be show that if F is surjective, if F hits everything over in B, then you actually get an equality here. So how can we say it? And this sign can be replaced by an equal sign with equality. Okay, interesting. So let's go ahead and start trying to prove this. So we'll start with number 1. Okay. I'll just remind the reader what we're trying to show. So we're trying to show this statement. Just the inclusion here. So that's a subset of T. That's what we're trying to show. Where do we start? hopefully you are well aware where to start here by now. What do we have here? A subset containment, right? Set containment. So we take an arbitrary element of here. Should we call it A or B? Let's see. Where does this live? I suppose this one lives over in B. So let's call it B. So let B be an arbitrary element of this one. So let this be arbitrary. What does it mean? This is going to be a little bit tricky. So we'll have to kind of do one layer at a time. But again, I'm just going to try to unravel this definition. Because that's really the only thing I can think of here. So what does it mean for B to be in here? Remember, f of something, what is that? That's our direct image. So that's our image, right? So what is this, like, what does f of s mean? Let's just recall that. It's just a set of all, like, f of a for a and s. Okay. So it's this means B is f of a for a in f inverse of t, right? So we're just writing down a definition of the direct image first. Start with the direct image. Then let's just write that down. So B equals f of something. So f of a for a in whatever this thing is, f inverse of t. Okay, so we've done kind of one layer at a time. Don't try to make sense of this whole thing at once. I mean, you could, but if you're thinking harder, you need to probably. So we did one step. Now we can keep going. So let's keep unraveling. What does this mean? So this is the definition of direct image. But since A is in f inverse of t, what does that mean? Well, it means that f of a is in t. F of a is in t, right? Okay. I think we've unraveled this definition as much as we can. So let's reassess things. So what are we trying to do? We're trying to show that B is in T. Wait a second, but B is f of A. F of A is in T. That was easy. We're basically done. How should we say this? But f of A is B. This is really the power of, just knowing the definitions really well. That's 90% of writing good proofs, just knowing the definition. Like, it really is. So f of A is B. So that means that B is in T. Okay. There we go. Let's look at part 2. So are we ready to do part 2? Yeah, we just proved that statement, right? So what's part 2? Let's just write down what we're trying to do. So we're trying to show the following. So if f is surjective, implies that it's an equality, right? So in other words, the reverse. So we always have this direction, right? So what we want to show is the reverse inclusion. So if f is surjective, we automatically have this. We also get this inclusion, and that will show that they're equal, right? Okay, so this is what we want to prove. Where do we start? We start by just saying take an arbitrary element of t, let B be in t, and now I'm kind of stuck, to be honest. So we can't unravel anything anymore. And so this is a bit tricky. We need to use the fact that f is surjective somehow. We need to show that B actually lives in this more complicated looking set. So this is where I can't really do anything more over here. Let's actually take a look at this set on the right side. Maybe I'll just over in the margin. I'll try to write my thoughts. So what do we need? We need to show this B is in this set over here. What does it mean to be in this set? I.e., it means that B is It's in a direct image. It's in the image, right, of the f of this thing, right? So it means that b is f of a for some a in here. Okay, so how do we show that? B is f of a. This b that we're starting, which is arbitrary b. We need to show it's f of a for some a in this set. Let's think for a second. I'm not sure I can do that. But wait, I'm forgetting something. So f is surjective. Let's try to leverage that somehow. So what does it mean to be surjective? Let's remind ourselves. What does it mean to be surjective? It means for every b and b, there exists an a and a, such that f of a is b. There's something mapping to everything in b, including this b that we started with. So maybe that's the idea. So since f is surjective, what does that mean? It means there exists an a in capital A such that f of a is b. Right? Okay. Now what? Well, we need to show that this A is in this set. But wait a second, it is, right? Because what does it mean to be in this set? It means that f of a lands in T, but b is in T. F of a is b and b is in T. So I think we can see how to connect this all. So that's what it means to be surjective. Since b is in T, we really do need to fact that it's surjective, though. Hope you can appreciate that as we're going through here. So since b is in T, a is in f inverse of T, just by definition. By definition of the inverse image of inverse image. Okay. Okay, and then we just reverse this, right? So then since f of a is b, what does that mean? Well, it follows that b is in the direct image of, so b is in the image of f inverse of T. Just by definition of image. Of the direct image this time, or image. Okay, and we're done. That was a bit tricky. So, we only get this reverse inclusion necessarily if f is surjective. We very strongly use that fact in the proof. Without that, I don't think we'd be able to show this. In fact, we wouldn't be able to show this in general. Okay, so maybe to close out, I just want to note something really interesting. So often when you have a result like this, you can think of the following way. So we have a definition of surjective, right? So I just jotted it down over there. In fact, we could actually use this result that we have. So in fact, this result we just proved can be extended. So I'll tell you what I mean. To give a different characterization of surjective, so characterization. In other words, some notion to, like, totally equivalent to surjective. So in other words, you can alternatively define surjective even to mean the following. So it's like an alternative definition. That's what I mean. So here's what I mean. F is surjective if and only if. So if and only if, double arrow, equivalency here, if for all T and B, so that's the extension I mean, so you have to say for all T and B, you get this. You get an equality, sorry. So for all T and B, you get f of f inverse of T equals T. Okay, and this turns out to be a kind of fancy looking equivalent definition of surjective. It's really cool. So if you want, you can define surjective this way instead of this way, and it's totally equivalent. Let's prove that. So yeah, why is that equivalent? What are we trying to prove? So it's a double arrow here. So it's a implication in both directions, right? That biconditional, just remember, biconditional, P if and only if Q is equivalent to P implies Q and Q implies P. Right? So let's try to prove this first. So if F is surjective, then you get this. Okay. Wait a second. I think that's what we just did, right? Because T is totally arbitrary here. So we did that. We did this. So we did that part. What about the reverse? So we really want to say, the only way you can get this for having for all T is if F is surjective. So the reverse direction, what do we want to show? We want to show that if you assume this property about F, that forces F to be surjective. So we don't know F is surjective. It's just a function. But if this property holds for all T, that forces F to be surjective. That sounds a little bit tricky. I don't think it'll be too tricky, though. But here's how we would start. So suppose this, right? So suppose, let me just restate that. This will be the last proof for it. So suppose that for all T in B, F of F inverse of T is T. For all T and B. And what are we trying to show? We're trying to show that F is surjective. How would we show F is surjective? Well, we would have to demonstrate this definition always holds. So we have to show that for all B in B, there's going to be something mapping over to it. So let's go ahead and start with that. So we're supposing that, and we want to show for all B something is true. So let's take an arbitrary B, little b in B. So we'll let that be arbitrary. Okay. How are we gonna find an A that maps to that B? That's our goal. So somehow we're gonna have to use this, and this is pretty flexible, right? So it's saying that it's true for all T. So we can even pick we can pick whatever subsets of B we need that will help us with this. Right now I can only see one subset of B. The single element set B, right? The little b. So maybe what would that mean? So in particular, what do we know? We know that F of F inverse of little, the subset, just contain a single element B. What should that equal? It should equal, just right on the nose, this subset contain a single element B. So can we leverage that somehow? Right. We want to show there's some element mapping to B. What is this? This is saying F of something is this set. The image of this set is B. So I suppose it's just going to be, this is our candidate. So whatever this is that going to be an element mapping to B? Well, that's not an element, right, necessarily. It's F inverse of some subset, B. There could be a lot of things mapping over to B. There might not be anything mapping over to B. But yeah, this is our candidate here, right? So what could the problem be? The problem could be, well, what if this is just the empty set? Then we won't be able to find an element mapping over to B. But wait a second. It can't be the empty set because this equality is true, right? F of the empty set, that would be empty, but we're saying F of whatever this is B. So there's got to be at least something in there, right? So let's note that this set, F inverse of B, let's call that something. So F inverse of B, otherwise it's going to get too confusing probably, is non-empty. Is non-empty. Why? It's because F of that set is not empty, right? In particular, it's this, right? So there's got to be something in there, right? Because this is a set of all things that map over to here. What is in there? There could be a lot of things that map to B, right? So I suppose we need to choose one of them. So let's choose some element of this set S. So choose any A and S. Then what do we know? We know that F of A is going to map. So technically we can't say F of A is B yet. We just know that by definition of our image, F of A is going to map into this set, right? It's going to be some element of this set. But yeah, I mean, there's only one element of that set. So therefore F of A is equal to B. F of A is equal to B. And what does that prove? Well, we found an element. It's just one of the many elements in this set, which is non-empty. Great. So I think we're done. So therefore, F equals B, and what does that show? So F is surjective. Again, because B was arbitrary, we showed there's something mapping to it. Okay, so we demonstrated that a definition for surjective holds. Okay, given this property. Okay, so yeah, I guess that completes the proof. So very interesting. Yeah, we can actually use this as an alternative definition of surjective. Okay, so hopefully this was helpful. Let's end the video there. Thanks for watching.